project, Sam and I developed a program that takes in a Schlafli symbol and displays the corresponding polycode. And so, for those of you who are interested in that sort of thing, you can find this code on GitHub. It's written in C++, and we call it Schlafli draw. So this is what the program looks like here. Up in the top left corner, this is the Schlafli symbol, and you can enter in certain inputs which will give you different shapes. And they can also go into 3 dimensions, for example. So you'll see more about that. So what they look like. Schlafli symbols are of the form, we say p/q, r/s, and they're inside curly brackets, one number / another number, one number / another number, etc. We say that each term is the set of numbers separated by a comma. So you have p/q, that's one term. P and q aren't separate terms, but they're part of the same term. And each term can have either 1 or 2 components. So restrictions on what you can do. P and Q, we say they must be natural numbers, so 1, 2, 3. And we also say that Q has to be less than or equal to P over 2. And it's actually possible that you'll get something valid if Q doesn't fit that criterion, but it's much more convenient for certain formulae if Q is less than or equal to P over 2. So we're just going to say that you have to do it that way. And the last thing before we really get started is dimension. Schlafli symbols work for any dimension, and the number of terms determines the dimension of the polytope. So if you have n terms, you're going to get an n+1 dimensional polytope. So the empty Schlafli symbol, which is this pair of brackets right there, it has 0 terms. 0 + 1 is just 1 dimensional. 5, 8, and 5 halves. I'll show you what those look like. You have 5, 8, 5 halves. Even though this one has 2 numbers, it's still only got 1 term, so they're all 2-dimensional. Another thing that I'll note right now, even though I say 5 halves, the 5/2 isn't technically a fraction. It looks like 1 and it sort of behaves like 1, but it's not actually the same thing. And then 5, 3, you'll notice the comma, they have 2 terms. 2 + 1 is 3-dimensional, and so on.
That's why you have to have a dimension greater than 0, because if you had 0 dimensions, you need -1 terms.
Exactly. So first dimension, not really too much of interest. It's just the empty Schlafli symbol. Line segment, pretty boring. This is also what you get actually if you put in the number 2. Effectively, the number 2 in a Schlafli symbol is the same as having nothing there. So 2D is where it starts to get kind of fun. In 2 dimensions, you can use a Schlafli symbol to represent a regular polygon. And so the first letter P, for any polygon, that just represents the number of sides on the shape. And Q, we'll get to that in a moment. If you don't specify Q, it's assumed to be 1. So in this case, 3 is actually 3/1, 4 is 4/1, but we ignore it. So 3, that means it's going to have 3 sides, and since it's regular, that gives us enough information to figure out exactly what it is. It's an equilateral triangle. 4 is a square, not just any rectangle, but specifically a square. 5 is a pentagon, and as you go up, you just keep adding more and more sides. You notice as you put in larger and larger numbers, it's closer and closer to a circle. You can also define what are called star polygons, however. And so the number P, not actually the number of sides, but more specifically it's the number of vertices. And the second number determines how we connect those. So generally, to generate the polygon from its Schlafli symbol, you lay out P points on a circle and connect every qth one. So what does that mean? For example, let's look at first the pentagon. We lay out 5, because it's Schlafli symbol 5, we lay out 5 points, and then just connect adjacent points. We connect every first point, so we get that. However, if I do 5/2, we'll be connecting every second point, or every other one. So if we start here, instead of connecting to that point, we'll be connecting to 1, 2, that point. So it'll be that point to that point, that point to that point, that point to that point, down to that point, and then back up to there. And so what that's going to look like is the pentagram here. And so the pentagram is the simplest star polygon, Schlafli symbol 5-2, and you draw it in exactly the way I just showed you. And a neat little term, the density of a polygon is basically the number of times that its boundary wraps around the center point in a certain direction. And you can determine it by tracing the boundary, and the way you do that is you basically draw sort of an imaginary line or ray from the center to any vertex. Let's use this one. So there's an imaginary line there. Then, starting from that vertex, follow the boundary around, and every time you touch that line, increment your count by 1. So we start out, Okay. Moving over, we cross it once there, so that's 1, 2, 3, and here we just touch the line at the vertex. So in this case, the density of this guy is 4. And so the density of all regular, what are called convex ones, like the pentagon here, the density of these guys is just 1. The term convex also, for people who may not know, basically what that means, you say that something is convex if you cannot pick any 2 points inside the figure such that the line connecting those 2 points goes outside of the figure. So for example, this guy is convex because for any 2 points in here I pick, the line segment's always going to be inside of it. To contrast, the pentagram here, this is not convex. If I pick, say, this point and that point, the line segment goes outside of the figure right there. So that's what we mean when we say something is convex. And so, how can you determine stuff about the polytope from the Schlafli symbol? That's the important thing. And you can get quite a few things just from looking at those numbers. For example, as long as you follow the restriction, the density is just Q. However, what if you don't follow the restriction? I mentioned that you could put in numbers like 3. 3 is greater than 5/2, so that doesn't follow our restriction, but it does still give us a valid polygon. The reason this happens is because now, instead of connecting every second vertex, we're connecting every third vertex. So if we started here, we would go 1, 2, 3. So we draw this line first. Then from here we go 1, 2, 3, and then we draw that line. And so what actually happens is we end up just drawing the same thing backwards. So we end up with the exact same thing that the 5/2's done. And for example, the 7/2's gone also. That's going to be the same as the 7/5's gone because you're drawing the same thing in reverse.
Reverse meaning like counterclockwise versus clockwise.
Right. So the next thing to look at is how P and Q relate and what that tells us. So there are 3 cases that we care about. We say that either P is relatively prime with Q, meaning that they don't share any factors besides 1, or that could not be the case. They could share a common factor. Or the third case, which is actually a special case of the second one, Q is exactly P over 2. And so each of these cases is going to give us a different type of polygon. The first case is the simplest one. In this case, the polygon is just one continuous line connecting all the vertices. So you can see, in this case, even 7/5 or 7/2. 7 and 2 don't share any factors. So you can see there's just one line right here going around the entire thing.
And 1 is considered relatively prime anything, right?
Exactly.
So 7, 1 reference.
So examples are 5/2, and as Mr. Drick says, all regular convex ones like this. The guys you normally think of when you think of a regular polygon. If they share a factor, it gets a little bit more interesting. So let's look at the hexagon here, the sixagon. What happens if you connect, well, if you connect every first vertex, you get this. But if you connect every second vertex, let's see what happens. You start here, you go 1, 2, you go there, 1, 2, you go there, 1, 2, you get back here. but you haven't touched all the vertices yet. You've left this one, and this one untouched. So how do you deal with that? What you do is then you have to start over at all of the vertices that you haven't yet gotten to, and keep doing it until you have hit all the vertices. And so in this case, it's going to look like this. What exactly happens, more precisely, is if the greatest common factor, you say the greatest common factor of P and Q is G. In that case, you're going to get an intersection of what I'm going to call lesser polygons, which are polygons that, for example, in this case, the triangle, your overall polygon is composed of two intersecting triangles. Specifically, you're going to get G intersecting the factored form of P and Q gons. So for 6-2, you have 2, G is equal to 2, so you get 2 intersecting 3/1 gons, or triangles. Another example would be, say, 8/2. Again, your greatest common factor is 2. Factor that out, you get 4. You're going to get 2 intersecting squares. And the program has a handy color option where it highlights each of the squares in different colors, so you can see, yeah, that's actually 2 different squares. And lastly, your lesser polygons don't actually have to be quite as simple as this. They can be star polygons. For example, let's look at 10/4. In this case, the greatest common factor isn't the entire bottom number, the entire cube. It's just 2. When you factor out 2, you're going to get 5/2. And so you're actually going to get 2 intersecting pentagrams. 10/4, you get that. So it's rather hard to see right now, but if I flip the colors, you can pretty clearly see there's one in green, there's one in red. And as they overlap, they form this larger, more complicated solid. Also, an interesting thing to show you, here's the 7 halves gon, which in my opinion is the creepiest one. It's just sort of unnerving. It doesn't really look right. If you look here at the 7/3, right there in the middle there, that is in fact a 7 halves gon. Following that line there. But I haven't seen any math to do with that, so I don't actually know how it works, unfortunately. Wow. And so the last case, Q is equal to P/2. This is just, again, a special case where your greatest common factor is P/2. What's going to happen is, when you factor that out, you're going to get P/2 2 gons. And remember that 2 is effectively nothing. So you're just going to get P/2 empty set gons, or line segments, connecting the opposite vertices. And so in that case, if we do 6/3, 3 is exactly half of 6. So we're going to get 3 line segments. And this is called the degenerate case. And here in the colors, you can see each of the 3 different line segments. So before we move on, I think it would be helpful just to look at the 8 gon, because it very nicely emphasizes all the different cases. Here's your first case, which we sort of mentioned implicitly, where Q is equal to 1. You get your, what you commonly think of as regular polygon. If we do 8/2, you factor out 2 and you get 2 intersecting squares. 8 and 3 are relatively prime, so you just get one continuous line forming a pretty cool shape. And 8/4 is a degenerate case. Alright, so now we get to move on to a higher dimension. So we know how 2D stuff works, but it's also possible to do 3D stuff by adding in another term. One more term means one more dimension, so 2 terms is 3-dimensional. We say that the 2 numbers in that term instead of P and Q are R and S. And for the moment, we're going to be ignoring S. We're just going to say it's equal to 1, and we'll add it in later. So the Schlafli symbol looks like P/Q, R/S. And the way you parse this is P and Q represent each face of the polyhedron, and R is the number of faces around every vertex, and S tells you how the faces are connected, but again, we'll get to that later. So as an example, the tetrahedron, shown here, you can see each face is a triangle, which has 3 sides, so that's just a 3 gon, we know that already. And around every vertex, for example, here you have 1, 2, 3 faces. So you have 3 around each vertex. And therefore the Schlafli symbol for a tetrahedron is 3, 3. So plugging that into the program, you see right there rotating with pretty colors is a tetrahedron. And that is what the edges look like without any faces on them. So polygon. Woo. So let's see how. So polydrons, basically, we can use these to create some of the possible polyhedra. And I'm going to use these, and then I'm going to have you guys use these to build these polyhedra from the definition of the Schlafli symbol. So what we're going to do is we're going to start with a tetrahedron, because we already know what that looks like. And it's got Schlafli symbol 3, 3. So we're going to need 3 trigons or triangles around every vertex. So the way you do this is you take triangles, different colors. So you take triangles.
We'll need the light up front now that he's showing you stuff. Would that be helpful or not?
Yeah. It's kind of like. So you have these triangles. So pick one triangle to be sort of your base starting triangle, and then pick a vertex on that triangle and start satisfying the requirements. So let's look at the top vertex of this one. It's only got 1 triangle around it right now, so we add on another. Now it has 2, and we add on another. So now it has all 3 of the required ones. But the problem is you'll notice the vertex isn't fully surrounded, and if we look at another vertex, say that one, that vertex has 2, but when I put on the last one down here, we have this shape, but it doesn't fully satisfy the requirements. This vertex up here doesn't have 3 triangles around it, but if I tried to put a triangle, say here, to fix that, this vertex would then have 4 triangles around it, so it doesn't work. So the way it deals with that is these triangles bend or fold up into the 3rd dimension, and they meet each other. So this vertex up here was once those 3 separate vertices, and you have a complete closed figure. And so you can do the same thing with a cube. The cube is going to be 4, 3. That's 3 foregons or squares around every vertex. Put these together. Once you get 3 around a vertex, bend up. And then sort of go about filling in the holes. It's easier for us rather than a computer because we can sort of see what it's supposed to look like and where things should go. This was one of the things that we had to deal with when we were making this program, how to generate 3D shapes from the symbol. And you plug it in, and you get this nice figure that satisfies all the requirements. So now I'm going to ask you guys to try to figure out what a 3, foregon is going to be by building it out of polydrons from this requirement and seeing what comes out. So
Each
polydrons
group
are
should
there.
pick some and share and discuss.
Wait, okay. You have 3, alright, so you have 3, 4 of them every face, and every vertex.
Got it. Don't worry. Alright.
Oh, it's cute and small.
First.
No, I already.
What does it look like?
Oh.
So what does it end up being?
D8.
You were first, but they have 3. They have 4.
Ah, yeah, we win.
So
They cheated.
that's possibly true. But I don't know, yeah. So I think yours is a bit closer. So yeah, as they have figured out, when you build it up from that definition, you get an octahedron here. And so, yep, that's an octahedron. You have, as you can see, you have triangles at the faces, that's 3, and around every vertex, you have 4 of them. So you can build 2 more polyhedra out of polydrons using this. I'm not going to ask you to do them because they take ages. But they're the dodecahedron, which is 5, 3. Nope, that's 5 3. 5,
You can at
3.
least look at what one vertex of it would look like.
You could do that if you want to pull out some, in this case, pentagons and stick 3 of them together. You get the dodecahedron, which is this, or in configuration. You can see that.
Yeah, this will be easier now. Right?
So, you have that. You also have 3, 5, which is the icosahedron. Looks like that or that. Just to show you, here's what the octahedron looks like. The colors are randomly generated, so sometimes they look good, sometimes they don't. You've already seen the tetrahedron and the last one is the cube.
That's so negative.
This guy right here. All right. So, now you'll notice we have polytopes for 3, 3, 3, 4, and 3, 5. Even sort of 3, 2. Because remember 2 isn't really anything, so 3, 2 is just a 2-dimensional triangle. It's a little bit sketchy. So, what happens if we try to continue the pattern and build a 3, 6 gon? Try that.
It's gonna be flat. It's not gonna work.
We'll stop you after a few years.
Just goes on for I'm running into a wall.
Do it. Or use default, or it's too late.
Okay, guys, let's just keep it going. It's gonna work. I don't know that it's not gonna work a certain amount of time.
Oh yeah, I guess we should
Getting anywhere. Higher form. Yeah. Exactly. I'm not a shape I want.
Put 7 together?
We're getting there. We're getting closer.
Really? Yeah, they're good.
Yeah. So what people are realizing right about now is that this isn't going to stop. Because what happens, if you look at Lydia's beautifully made quote there, what happens is you start out with 1 vertex, you put 6 around it. At that point, you have filled the space around it exactly. There's no room for it to hold up. So, but on the other hand, all the vertices of the triangle that aren't that center vertex, those haven't yet filled the requirements, so you're not done. You have to keep on putting on triangles to those. But every vertex is going to end up looking like that center one. So effectively, you're going to be doing that for infinite time, assuming you had that much time to spare.
Work for hyperbolic space, like 3, 7?
Yes, they do. We just didn't look at that. Yeah. So, what you're going to get is you're going to get a tessellation of the plane if you try to do that. And so, the notation PQRS, which normally we think of as a 3-dimensional shape, could also work out for the 2-dimensional tessellation. So the first one you've seen is this one, 3, 6, which is the triangular tessellation. There are in fact 2 more that work, and that's it. You have the square tessellation, 4, 4, 4 squares around every corner, and the hexagonal tessellation, 6, 3, which is honeycombs. You'll notice actually that's contained within the triangular tessellation. Like here's one hexagon there, there's another. So one thing that when we were coding we had to figure out was, okay, if we get a Schlafli symbol with 2 terms, how do we know if it's a tessellation or a 3D solid? Because we draw them in different ways. One's 2-dimensional, one's 3-dimensional. And so the solution that we came up with is, it lies in this property called the angle defect, which is the amount by which the interior angles of your faces differ from 360 degrees, or fail to add up to 360 degrees. So one thing that's a little bit tricky about that is that it's the amount by which they fail, meaning that if you have less than 360 degrees, they fail by a positive number, so your angle defect is positive. Your angle defect is going to be negative if you have too many. So it's a little bit counterintuitive. But as you can see here, this is what you get when you're trying to make a tetrahedron. And so you have 3 triangles here. They add up to 180 degrees. But this space here is coincidentally also 180 degrees. These happen to fill it exactly halfway. So you've got an angle defect of the same size, 180 degrees. And so that's why the triangles fold up to compensate for that. For tessellations, however, if you do it with 6 triangles, they fill up the space exactly. And so your angle defect is exactly 0. Therefore, they don't fold and they go out to infinity. Because they don't fold, the vertices never meet each other to terminate. So that's why, that's one of the reasons it'll go out infinitely. So in general, your Schlafli symbol is going to have, if it's got 2 terms, it's going to be a tessellation if the angle defect is exactly 0. And it'll be some sort of 3D solid if the angle defect is greater than 0. If the angle defect is less than 0, we didn't look at that at all. It is kind of messy. It goes into hyperbolic space. And so our program can certainly not do that.
If you put 7 together at each vertex, you'd get this really weird, foldy, wavy thing, which you guys looked at some models of hyperbolic spaces, like, do you see those woven models that Steve showed you those? Yeah, those are more precise because the cloth obviously is more flexible than the polygons. But you get the same thing, but more continuously when you use cloth.
I really got to throw those at the tape.
You get the throw.
He was advertising it. You got to throw things at the teacher. Anyways, so the last thing is, Schlafli symbols can actually draw a few more things than just the platonic solids that we've already seen. So in addition to those 5, we can also specify what are called the Kepler-Poinsot polyhedra, which are regular also, but they're non-convex. And they have star polygons as either their P/Q or their R/S. Unfortunately, our program, since we have actually been doing the displaying ourselves as well as just making it, we didn't use some display library. These turned out to be much too hard for us to display, so we're unable to put these out so that they look right. They actually do exist in the code, and we can display their edges, but the faces overlap, and so we can't show you with the program. So instead, we're going to be using pictures from Wikipedia, and we'll be presenting them in what are called dual pairs, which we'll explain afterwards. So the first 2 are the small stellated dodecahedron and the great dodecahedron. So this guy, it has Schlafli symbol 5/2, 5. What that means is its faces are actually pentagrams, and there are 5 of them at each vertex. Looking here, you can see one of the faces is right there. That's one of its faces. And pick a vertex, say this one. You can see 1, 2, 3, 4, 5 faces meet there. The other guy, the great dodecahedron, that's my personal favorite. It's got Schlafli symbol 5, 5 halves. What that means is that its faces are pentagons. And so, for example, this big thing here, that's one of its faces. So they're almost as big as the thing itself. And the 5 halves, that means that there are 5 faces meeting at every vertex, but they're connected alternately. You'll notice here, if you look at this vertex, you have your 5 faces, but this face here, it connects at that edge and that edge, skipping that one there. So that's what it means to have an S that's not equal to 1. In this case, S is 2. The other 2 are the great stellated dodecahedron, 5 halves 3. This one's a little bit harder to see. It also has pentagrammal faces. It's pretty obscured here, but there's one right there. And as you can see, it meets 3 at each vertex. The last one is the great icosahedron, 3, 5 halves. It actually has triangular faces, which are also hard to see. One of them, for example, is right there. And they meet alternatingly at every vertex, as you can see right there. So those are the so we haven't been able to make these work exactly right. However, because the great dodecahedron is my favorite, I did a little bit of work on it. So this almost works. You can see, if you know what it looks like, you can see it here. You notice the triangles aren't displaying entirely right, but you can sort of see it. If I turn off faces, you notice actually this has the same edge configuration as the icosahedron. To my knowledge, I don't know why that is. Makes it a little bit sad because you can't display it properly using just faces, edges. Here you'll notice if I do 5 halves, 3, there's your great stellated dodecahedron. 5 halves, 5 is your small stellated dodecahedron. And in this case, 3, 5 halves, that has the same edge configuration. That's your stellated icosahedron, or your great icosahedron. It's got the same edge configuration as the small stellated dodecahedron. Again, so duals. Duals, every polyhedron has this thing called a dual. And so a dual is basically the polyhedron that you get when you connect the midpoints of the sides of your original polyhedron such that they become the vertices of the new one. For example, the octahedron and the square are, or the cube, sorry, are duals. We have a cube here. We connect the midpoints there, you see, like that. Yeah, that was clear, right? You have the midpoints, you connect them to every adjacent one, and you get, that looks like an octahedron.
Well, there's more to be said there. It's how you connect them, because there's obviously some vertices we didn't connect. You connect those that correspond to faces that meet at a vertex. So like, for instance, you got that lower left corner of the cube, and there are 3 faces that meet there, and those are the 3 that get connected to each other, which is why you're replacing vertices with faces and faces with vertices. That's why it's called dual. You're flipping those 2.
Exactly. So basically what Mr. Drix just said. You'll notice that the number of edges that a face has is equal to the number of edges that meet at each of the corners of the original polyhedron. So, as he said, you have a corner right here. You have 3 edges meeting there, 1, 2, 3. And so the face of the octahedron has 1, 2, 3 sides. And similarly, the number of edges, or faces specifically, that meet at each of the dual's vertices is going to be the number of faces adjacent to each face of the original. For example, on the octahedron, you have 4 faces meeting at every vertex, right? 1, 2, 3, 4. And the square has 1, 2, 3, 4 faces adjacent to it. And so you'll notice that's actually the number of sides on the face, because each edge that the face has is going to be shared with 1 additional face. So if this were 5-sided, it would have 5 faces, and so its dual would have 5 connecting at every vertex. And so what that suggests is that the p-value of the dual is equal to the q-value of the original. That's saying that the type of face that it has is going to be determined by how many faces meet at the original's vertices, and vice versa. The q-value of the dual, the number of faces that, or the r-value of the dual, sorry. The number, I messed that up, sorry. The r-value of the dual, the number of faces that meet at every vertex, is going to be equal to the p-value of the original, the type of faces that it has. So it looks like basically that to get the dual, you would just flip the terms. And that's actually how it works. Otherwise I wouldn't be telling you that. And so you get the dual of the cube, which is 4, 3, is going to be flip those 3, 4, and you get the octahedron. So 2 more important definitions are facets and vertex figures. So this is getting a little bit more advanced, but we'll say that a facet of a regular polytope is the feature of that polytope of dimension 1 less than the polytope itself. So what that means is, for example, on a 3D polyhedron, its facets are going to be its 2D aspects, or its faces. So the cube here, the facets are squares. And the facets of those faces, for example, the facets of those faces for example, the triangle, are going to be just the edges. The vertex figure, there are a few definitions that mathy people use. We're going to say that the one that we use is it's the cross-section you get if you slice the polyhedron very close to a vertex. So to sort of visualize that, imagine yourself at one of the vertices. Quickly, here's a vertex of the tetrahedron. Imagine yourself at one of the vertices, sort of flowing down the edges a little bit and then cutting across. And so in this case, if you do it for a tetrahedron, you're going to end up with a triangle. You can go down a little bit and chop across, you get a triangle. So, good examples. The icosahedron has 5 triangles around every vertex. That's 3, 5. So if we look at that vertex there, and we flow down around it and then sort of cut across, we're going to be getting a pentagon. And one of the things that makes the icosahedron nice is that that pentagon right there, that really, really big one, is actually just sort of an extra large version of its vertex figure. Another helpful one to look at is the great dodecahedron, which we can't show you properly, but you'll notice here, you start at this vertex and you flow down a bit. When you cut across, you actually get a pentagram. And again, the reason it's kind of nice is because that right there is just a particularly large instance of its vertex figure. So now let's look at the cube, this guy here. Its facets, again, are going to be its faces, just the squares. Its vertex figure, this one's a little bit harder to see, but its vertex figure is going to be an equilateral triangle. If you go down and cut out, you're going to get an equilateral triangle. So just from this example, it sort of looks like the facet is going to be P/Q, dropping the last term, and the vertex figure is R/S, dropping the first term. The facet is 4, the first term, and the vertex figure is 3, the second term. And again, because I'm leading you through this, this is going to work for all 3D solids. And so what about two-dimensional stuff? Heading back down to 2D, if I do, for example, the pentagon, you can see that its facets are just its edges. We drop the last term. It's also the only term. We get nothing. We get just a line segment, which is exactly that. The vertex figure, if we start at a vertex and cut across, we're just going to get a line. And so dropping the first term, again, the only term, we get a line. So it looks like this still works. And in fact, it does. So generalizing to n dimensions, if you have an n-dimensional polytope with Schlafli symbol p, q, r, yz, its facets are going to be p, q, r, y, just dropping the z. Its vertex figure is going to be q, r, yz, dropping the p, the first term. And this is actually part of how Schlafli symbols are defined. And so, moving up in the world, basically everything we've mentioned so far either applies directly to or is generalizable to higher dimension stuff. For example, dual, with higher dimension stuff, you still do the exact same thing, you flip it. So if you have p, q, r, y, z, its dual is going to be y, z, r, q, p. And 4-dimensional stuff. So 4th dimensional polychora, you need 4 dimensions, so you're going to have 3 terms. And so the simplest example is what's called the 4 simplex. A simplex is basically the analog of a triangle or tetrahedron in n dimensions. And so it's got Schlafli symbol 3, 3, 3. What that means is that it has 3 tetrahedrons. It has 3, 3, 3-gons around every edge, rather than around every vertex. And so you can also do tessellations. Like in 2 and 3D, there's a 3D tessellation that shares the same notation as 4th dimensional polychora. In this case, that's the cubic honeycomb, shown there. It's got Schlafli symbol 4, 3, 4. And this is actually the only regular tessellation of 3D space. And in general, in n dimensions, what are called the tesseractic tessellations, which are tessellations of cube analogs, are generally the only, they're the only tessellation that exists in n-dimensional space. Fun stuff. So looking at this, you can see this is a tessellation composed of cubes. And around every edge, say that one, it's kind of hard to see, but around every edge you actually have 4 cubes. So a cube, if you remember, is a 4,3 gon. So the symbol for this is going to be 4, 3, 4, or just 4, 3, 4, and so it looks 4 dimensional. Pretty much the last thing is the tesseract. We've seen this a few times from other places in this class, but this is the analog of a cube in 4 dimensions. Its facets are cubes, and so it's composed of cubes, and around every edge there are 3. So in order to get this, we use Schlafli symbol 4, 3, 3. And so over on the side here, this is just what a tesseract would look like projected down onto the plane. Mr. Drix, I think, has mentioned the middle one and the big one. They're the same size, but this one's just further away in 4 space, so it looks smaller. This is actually a tesseract unfolded, the same way we would draw like a net for a cube. This is a tesseract unfolded into 3 dimensions. If you were 4-dimensional, presumably you could see some way to pick that up and make it work. And that's it.
Thank you. You can put yours in the pile for me so I can pick them up quickly.
Well, some more high.
And put the polygons away, please.